The percentage of power loss on a transformer due to heat typically falls within the range of 1 to 3%. This power loss, often referred to as copper loss or I2R loss, is primarily due to the electrical resistance of the transformer windings. When current flows through these windings, which are typically made of copper, some of the electrical energy is converted into heat due to the resistance. The amount of heat generated, and thus the power loss, is proportional to the square of the current flowing through the windings and the resistance of the windings. This relationship is expressed by the formula P equals I squared R, where P is the power loss in watts, I is the current in amps, and R is the resistance in ohms. Several sources provide detailed information on transformer power losses. Firstly, the National Electrical Manufacturers Association, or NEMA, sets standards that specify typical power loss values for different types of transformers. These standards ensure that transformers meet certain efficiency requirements and that the power losses are within acceptable limits. NEMA standards can be found in their publications and online resources. Secondly, transformer manufacturers provide data sheets for their products, which include detailed information on power losses. These data sheets typically specify the no-load loss, also known as core loss or iron loss, and the full load loss, which includes both core loss and copper loss. The data sheets may also provide information on how the power loss varies with temperature and load. Examining these data sheets is essential for determining the specific power loss characteristics of a particular transformer. Thirdly, electrical engineering reference books and textbooks contain comprehensive information on transformer losses, including heat losses. These resources provide theoretical explanations of the factors that contribute to power loss and practical guidance on how to calculate and minimize these losses. They often include detailed discussions of copper loss, core loss, eddy current loss, and hysteresis loss. Furthermore, it's important to understand the relationship between transformer efficiency and power loss. Transformers with higher efficiency have lower power losses and, therefore, generate less heat. The efficiency of a transformer is defined as the ratio of the output power to the input power, expressed as a percentage. The difference between the input power and the output power represents the power loss. Therefore, a transformer with an efficiency of 98% will have a power loss of 2%. This means that for every 100 watts of input power, 2 watts are lost as heat. To minimize power loss due to heat in a transformer, several strategies can be employed. Firstly, using larger conductor sizes for the windings can reduce the resistance and therefore the copper loss. Secondly, using high-quality core materials can minimize core loss. Thirdly, ensuring proper ventilation and cooling can help to dissipate the heat generated by the transformer. Fourthly, operating the transformer at or near its rated voltage and current can minimize losses. Overloading a transformer can significantly increase power loss and heat generation. Fifthly, regularly inspecting and maintaining the transformer can help to identify and address any potential problems that could lead to increased power loss. This includes checking the insulation, connections, and cooling system. Understanding the percentage of power loss due to heat in a transformer is crucial for designing and operating electrical systems efficiently. By knowing the typical power loss values and the factors that influence them, engineers can select the appropriate transformers for their applications and implement strategies to minimize losses and improve overall system efficiency. The topic of transformer losses involves several key aspects that are important to understand for efficient electrical system design and operation. These aspects include the types of losses, factors affecting losses, methods to calculate losses, and strategies for minimizing losses. Firstly, there are primarily two types of losses in a transformer: core losses and copper losses. Core losses, also known as iron losses, occur in the transformer core due to the alternating magnetic flux. They consist of two components: hysteresis losses and eddy current losses. Hysteresis losses are caused by the energy required to repeatedly magnetize and demagnetize the core material during each alternating current cycle. These losses depend on the frequency of the alternating current, the magnetic flux density, and the properties of the core material. Eddy current losses are caused by circulating currents induced in the core material by the changing magnetic field. These currents flow in closed loops within the core, generating heat and wasting energy. Eddy current losses depend on the frequency of the alternating current, the magnetic flux density, the thickness of the core laminations, and the resistivity of the core material. Copper losses, also known as I2R losses, occur in the transformer windings due to the resistance of the copper conductors. These losses are proportional to the square of the current flowing through the windings and the resistance of the windings. Copper losses increase with the load in the transformer and are a significant source of heat generation. Secondly, several factors can affect transformer losses. The load on the transformer is a primary factor. As the load increases, the current flowing through the windings increases, resulting in higher copper losses. The voltage and frequency of the applied power also affect losses. Higher voltages can lead to increased core losses, while higher frequencies can increase both core and copper losses. The temperature of the transformer windings and core also plays a role. As the temperature increases, the resistance of the windings increases, leading to higher copper losses. Additionally, the properties of the core material, such as its permeability and hysteresis characteristics, affect core losses. Thirdly, various methods can be used to calculate transformer losses. The most common method involves using the equivalent circuit of the transformer. The equivalent circuit represents the transformer's electrical characteristics using a combination of resistances, reactances, and voltage sources. By analyzing the equivalent circuit, engineers can calculate the core losses, copper losses, and overall efficiency of the transformer. Another method involves performing open circuits and short circuit tests on the transformer. The open circuit test measures the core losses, while the short circuit test measures the copper losses. These tests provide accurate data that can be used to determine the transformer's efficiency. Furthermore, transformer manufacturers often provide data sheets that include information on the transformer's losses and efficiency. These data sheets are based on testing and analysis performed by the manufacturer and can be a valuable resource for engineers. Fourthly, several strategies can be employed to minimize transformer losses. Using high-quality core materials with low hysteresis and eddy current losses is essential. These materials are typically made of silicon steel or amorphous alloys. Reducing the thickness of the core laminations can minimize eddy current losses. Thinner laminations result in shorter current paths and lower circulating currents. Using larger conductor sizes for the windings can reduce the resistance and, therefore, the copper losses. Larger conductors have lower resistance, resulting in less heat generation. Optimizing the transformer's design to minimize leakage reactance can also reduce losses. Leakage reactance is the reactance caused by the magnetic flux that does not link both the primary and secondary windings. Minimizing leakage reactance improves the transformer's voltage regulation and efficiency. Ensuring proper ventilation and cooling can help to dissipate the heat generated by the transformer. Adequate cooling prevents overheating and reduces the temperature of the windings and core, which in turn reduces losses. Operating the transformer at or near its rated voltage and current can minimize losses. Overloading a transformer can significantly increase power loss and heat generation. Regularly inspecting and maintaining the transformer can help to identify and address any potential problems that could lead to increased power loss. This includes checking the insulation, connections, and cooling system. In summary, understanding the different types of transformer losses, the factors that affect them, the methods for calculating them, and the strategies for minimizing them is crucial for designing and operating efficient electrical systems. By implementing these strategies, engineers can reduce power losses, improve transformer efficiency, and save energy. Another aspect of transformer power loss relates to the different standards and regulations that govern transformer efficiency. These standards and regulations are designed to promote energy conservation and reduce greenhouse gas emissions. Several organizations and government agencies have established standards for transformer efficiency. The National Electrical Manufacturers Association, NEMA, is a leading organization that develops standards for electrical equipment, including transformers. NEMA standards specify minimum efficiency levels for different types of transformers. The United States Department of Energy, DOE, has also established energy efficiency standards for transformers. These standards are based on the Energy Policy and Conservation Act and require manufacturers to meet certain minimum efficiency levels. The European Union has also implemented energy efficiency standards for transformers through the Eco-Design Directive. This directive sets minimum efficiency requirements for transformers sold in the European Union. These standards and regulations vary depending on the type and size of the transformer, as well as the application. They typically specify minimum efficiency levels at different load points, such as 50% load, 75% load, and 100% load. To comply with these standards and regulations, transformer manufacturers must design and produce transformers that meet the specified efficiency levels. This often involves using advanced materials, optimizing the transformer's design, and implementing efficient cooling techniques. Compliance with these standards and regulations is essential for selling transformers in certain markets and for ensuring that transformers operate efficiently. In addition to meeting minimum efficiency levels, some standards and regulations also require transformer manufacturers to provide information on the transformer's efficiency and losses. This information is typically included on the transformer's nameplate and in the manufacturer's data sheets. This information allows users to compare the efficiency of different transformers and select the most energy-efficient option for their application. Another important consideration is the life cycle cost of a transformer. While a more energy-efficient transformer may have a higher initial cost, it can often result in lower operating costs over its lifetime due to reduced energy consumption. Therefore, it is important to consider the total cost of ownership when selecting a transformer. In conclusion, understanding the different standards and regulations that govern transformer efficiency is crucial for designing and operating energy-efficient electrical systems. By complying with these standards and regulations, engineers can reduce power losses, improve transformer efficiency, and save energy. The practical applications of understanding and mitigating transformer power loss are wide-ranging and significant, impacting various industries and sectors. Firstly, in power distribution systems, transformers are used to step down voltage from high-voltage transmission lines to low-voltage distribution lines that supply power to homes, businesses, and industries. By using energy-efficient transformers in these systems, power losses can be minimized, resulting in significant energy savings and reduced greenhouse gas emissions. Secondly, in industrial facilities, transformers are used to power a wide range of equipment, including motors, drives, and lighting systems. By using energy-efficient transformers in these facilities, energy consumption can be reduced, leading to lower operating costs and improved profitability. Thirdly, in renewable energy systems, transformers are used to step up voltage from renewable energy sources, such as solar panels and wind turbines, to the high-voltage transmission grid. By using energy-efficient transformers in these systems, the overall efficiency of the renewable energy system can be improved, making it more economically viable. Fourthly, in data centers, transformers are used to power the servers and other equipment that store and process data. Data centers consume large amounts of energy, and by using energy-efficient transformers in these facilities, energy consumption can be significantly reduced. Fifthly, in transportation systems, transformers are used in electric vehicles and trains to convert electrical power from the grid or batteries to the voltage levels required by the vehicle's motors and other systems. By using energy-efficient transformers in these vehicles, the overall efficiency of the vehicle can be improved, leading to longer driving ranges and reduced energy consumption. Furthermore, understanding transformer power loss is crucial for designing and operating smart grids. Smart grids are advanced electrical grids that use digital technology to monitor and control the flow of electricity. By using sensors and data analytics, smart grids can optimize the operation of transformers and other grid components, reducing power losses and improving overall grid efficiency. In addition to these specific applications, understanding transformer power loss is also important for promoting energy conservation and sustainability. By reducing power losses in transformers, we can reduce the demand for electricity, which in turn reduces the need to build new power plants and extract fossil fuels. This helps to protect the environment and conserve natural resources. In conclusion, the practical applications of understanding and mitigating transformer power loss are vast and impactful. By implementing energy-efficient transformers and optimizing their operation, we can save energy, reduce greenhouse gas emissions, improve profitability, and promote sustainability. Moreover, there are emerging technologies and trends that are shaping the future of transformer design and operation, with a focus on further reducing power losses and improving efficiency. One such technology is the use of amorphous core transformers. Amorphous core transformers use a core material made of amorphous metal alloys, which have significantly lower hysteresis losses compared to traditional silicon steel core materials. This results in lower core losses and improved efficiency. Another emerging trend is the development of solid-state transformers. Solid-state transformers use power electronic devices to convert voltage and current, rather than relying on traditional magnetic cores and windings. Solid-state transformers offer several advantages, including smaller size, lighter weight, improved efficiency, and enhanced control capabilities. They can also provide power factor correction and harmonic filtering, further improving power quality. Furthermore, there is growing interest in the use of smart transformer technologies. Smart transformers incorporate sensors, communication devices, and control algorithms to monitor and optimize their performance. They can provide real-time data on voltage, current, temperature, and power losses, allowing operators to make informed decisions and optimize transformer operation. Smart transformers can also be integrated with smart grids, enabling advanced grid management capabilities. Another trend is the development of high-temperature superconducting transformers. High-temperature superconducting transformers use windings made of superconducting materials, which have zero electrical resistance at cryogenic temperatures. This eliminates copper losses in the windings, resulting in significantly improved efficiency. However, these transformers require cryogenic cooling systems, which can add complexity and cost. In addition to these technologies, there is also ongoing research and development in areas such as advanced core materials, optimized winding designs, and improved cooling techniques. These efforts are aimed at further reducing power losses and improving the overall efficiency of transformers. In conclusion, the future of transformer design and operation is being shaped by emerging technologies and trends that focus on reducing power losses, improving efficiency, and enhancing control capabilities. These advancements will play a crucial role in creating a more sustainable and energy-efficient electrical grid.